So, poslední lekcja jest trudno. So I want to start by explaining where the functional equation comes, at least for the zeta function, and to explain why, well, I will construct an L function associated to what I will call a modular form, and I will explain that it looks like a lot like the L function of an elliptic curve, and that will not prove but explain the functional equation for elliptic curves. So remember, we have, so the zeta function was something like this, and Euler product, which of course you can write also as a Dirichlet series. And the other function that I have introduced many more functions, but the only one that I have fully detailed is this one, the L function associated to an elliptic curve over the rational numbers, so which you can write as a product of 1 minus AP P minus S plus, well, I will write it like this, epsilon P 1 minus P S minus 1, the product over all P, and epsilon P is 1 in general and 0 if P divides the conductor. So that's just a way to rewrite what I wrote as a separate product. And the functional equation that they satisfy is, well, if you add the factor for zeta of S, the factor that we add is P to the minus S over 2, gamma of S over 2, zeta of S. For the L function, we add, well, there is a conductor, the conductor of the elliptic curve, and then there's a factor gamma that looks like this, 2 pi minus S gamma S. And then the functional equation can be written in a simple way. Here it's just that psi of 1 minus S is equal to psi of S. And here lambda of 2 minus S is equal to, there is a sign. So we prove at the same time analytic continuation, because those formula, the Euler product or the Dirichlet series, they converge only for real part of S sufficiently large. Here for a real part of S strictly greater than 1, and here for a real part of S strictly greater than 3/2. I didn't show this one, but it's not difficult with what we've done. So we show at the same time analytic continuation to the whole plan and the functional equation. So the principle is the following. In fact, both in some cases are built on Poisson's formula, which, well, I only need the simple Poisson formula, which states that the sum of values for n in Z of a nice function, I mean, that tends sufficiently quickly to 0, is equal to the sum of the value of its Fourier transform. So here I take the Fourier transform, I normalize it this way, f of u exponential 2 pi I u t du, that will be fu. So I put the 2 pi here, so otherwise you have a constant that comes here. And if you take another lattice and Z, you also have a constant that comes into, but I mean the volume of Z is 1, so there's no constant, that's the simplest. So if you apply this I define the theta function as the sum from n to z of exponential minus pi n squared u. So it's clear that the exponential minus is something that decreases sufficiently quickly, so you can apply the Poisson formula. So I don't give the detail of the computation, which is easy. The functional equation that you obtain is the following: theta of u minus 1 is square root of u times theta u. So it's just computing what is the Fourier transform. What happens is it's well known that this function exponential minus x squared is essentially an eigenvalue for the Fourier transform. So you get something that looks like this function. So if you write, I think I had done that. You can write this as an integral. You get actually an integral that is not theta, but where theta tilde is just, well, what comes into is just the sum, but only for positive n. So theta tilde is just theta of u minus 1 over 2. Okay, I think I have done this computer. Anyway, it's easy. What you write is the integral. Maybe I can redo that quickly because I see eyes opening. If you write p minus s, so the integral of exponential minus t s minus 1 dt times the sum. Okay, so that's just rewriting. That's just rewriting this function. Sorry, it's not ts, it's s over 2. So if I do that, what I do is I exchange sum and integral. You of course have to check that you have the right to do that. If you do that, you end up with the sum of the integral of so pi, so it's s over 2 here, pi minus 1 over 2 t over 2 n over n to the power s exponential minus t dt over t. So I spare 1 t here, and I make the obvious change of variables. So actually, it's not. I don't want to put t square here. I want to make the change of variables. I'll take the minus the 1/2. I'll take it outside. And so I have an n square here. So I will put u equal to that. So if I do that, I get the sum from n equals 0 to infinity of the integral of, so u s over 2. And here I get, well, exponential minus, so t is equal to n squared by u du over u. And so if I exchange again now the integral with the summation, I will get the integral of, well, the sum of exponential minus n squared by u n equals 1 to infinity, u s over 2 du over u. So that's this formula. Okay. Now, if I plug in the functional equation into this, that I will write directly. It's very easy. You get that theta tilde of u minus 1 is the square root of u theta tilde of u. And you get a small error, well, a correcting term, which is the square root of u minus 1. In some sense, you get this formula. So, well, I won't need that one again. So now the basic idea is that actually the functional equation will come from that equation. So I take this again, I will split the integral into, well, the integral from 0 to 1 plus the integral from 1 to infinity. I don't rewrite this. And what do I do? Well, in this integral, I change u to u minus 1. But only in the first integral. So here I get, once I make it, perhaps I should, well, I will call it the same. So I get the integral. So if I'm going from 0 to 1 and I exchange, I will get an integral from infinity to 1, but I will get a sign minus here, so I do both things at the same time, so I get the integral from 0 to infinity. Here, theta tilde of u minus 1. So here I get u minus s, and the du over u doesn't change because I've already put the sign in exchanging the extremities. So I get this plus, well, the same thing. This one I will write again. Theta tilde u s. So there is an s over 2 perhaps that I have not written. Here it's s over 2. So I get minus s over 2 du over u. This is basically that. And once we're there, what we do, of course, is we exchange with this formula. So the first integral will be, so I get the integral from 0 to infinity of, well, I will right away write those two together. So u s over 2 plus, so this is what comes from here. Now this one is this integral here, so I get a square root, so I get the square root of u, so u1 minus s over 2, since I multiply by this, du over u, and plus the integral of this term multiplied by this, so plus 1/2 of the integral from 1 to infinity of, well, u, so square root of u, that gives me 1 minus s over 2 du over u minus 1/2 of the integral from 1 to infinity of u minus s over 2 du over u. So this term is actually quite easy to compute. It's 1 over s minus 1, and this one is 1 minus s. And now if we look at this term, everything becomes quite nice because so all the computation is done for real part of S strictly greater than 1, of course. I've used convergence of the series and all that, so the computation is done for real part of S strictly greater than 1. But now I look at the formula, and I say that the formula defines an analytic function. Okay, this defines an entire function, and this has only a pole at S equals 1 and S equals 0. So it gives me the analytic continuation. Why is that? Is that this function it decreases extremely fast when, well, first, here it's bounded, the integral is bounded, there's no more singularities. And the function, so theta tilde is the sum for n at least 1. So when u goes to infinity, it is a function that decreases exponentially. Therefore, this integral at infinity is convergent for all values of S. And if you fix the, say, real part of S greater than something, it's uniformly convergent. So this defines an entire, this is clearly an entire function. Further, if you restrict S to a strip or even to a half plane, it's uniformly bounded. So that's what I called bounded in vertical strip. It means in all vertical strip, meaning something like this, it's uniformly bounded. And further, the expression of the function makes it clear that it's invariant under this change of variables, because if I exchange S and 1 minus S, those two gets exchanged, and here the S gets exchanged with the 1 minus S. Okay, so that proves the functional equation. This is the Riemann's proof. Well, Riemann gave several proofs in his paper, but that's the one that really extends, that really gives something in general. So you see that, in some sense, the essential point is the functional equation, is representing the zeta function as an integral of some function that satisfies, well, what I will soon call a modular equation.
What is the meaning that zeta corresponds to theta?
The meaning. Well, they are in some sense simply related. So, except that you notice that the pole comes from the fact that actually the zeta function is not exactly the Mellin transform of a modular form. It would be if here I would put theta, but then I would have to remove the poles, etc. So the relation is in fact not that simple. Surprisingly, the relation will be simpler for the elliptic curve. But on the other hand, it has to be a little more complicated because there is a pole, and essentially, at least conjecturally, it's the only zeta function that has a pole. Or those who have a pole factor by zeta. That's not proven, but that's conjectured. So that probably doesn't fully answer your question, but there's no, I don't think there is really a complete explanation of that.
Because theta feels like modular forms, and if they transform modular forms, we get something that looks not like zeta function, or like even zeta function, but more like elliptic curve, right?
Yes. It's because in some sense, this is not exactly the Mellin transform of a modular form. It is of something modified, and this modification, so analytically you see explain the pole.
It feels like something else on the floor.
Yes, I agree with that. But I don't think there is, no one has a full explanation for that. Perhaps finding a full explanation to that would give a clue to how to prove the Riemann hypothesis, but so it was, so Riemann is 19th century. The next step actually is to show, well, it is extremely difficult to extend the L function, any Hasse-Weil function. So again, I will write it. We can write it as a series like this, just expanding the Euler product. You notice that there's no conflict of notations. So a priori, if I expand this, I get a Dirichlet series with new coefficients. And here I have the coefficient for P, and it is the same with this, as this one. That's just an easy calculation. Now, the idea is that if we knew that in some sense this series with, so I'm just replacing the coefficients 1 by other coefficients. If we knew that some theta series with the coefficient an satisfied a nice property like this, we could prove the functional equation. So this is exactly the way it's done, except that the very highly non-obvious thing is that such a thing is true for elliptic curves over Q. So I want to explain what is modular form. Then we will associate, well, I will call F a modular form. We will associate the Dirichlet series. And what I will explain, this is where I will stop there, is that we obtain L series that looks really like this. And that's why there was for a long time the conjecture that they are the same. And that's the content of Weil's theorem. That I will just quote. I will give no clue even how you prove that. So modular forms are a classical object. They are defined as so holomorphic function on the upper half plane. So this is also called, well, in France we call it Poincaré upper half plane. I guess perhaps you would call it Lobachevsky's upper half plane, never mind. Imaginary part positive. And basically on H you have, well, the biggest group you can write that acts on this is the 2x2 matrices with positive determinant. And the action is that, well, to a matrix A, B, C, D, and Z, you associate AZ plus B over CZ plus D. You can also make act the full GL2, but then you need to take the two copies of the upper half plane. So I'll do it like this. And when do you call that a modular form? Well, the essential, so you have inside this, you have SL2Z, which is a discrete group. And actually, it's quite fundamental to observe that the quotient by SL2Z is naturally isomorphic. I will write it like this, to A1 of C, or C, it's C. It's just the J function of elliptic curves. You can compactify H by taking, well, I will write it like this. you imagine you have the half plane. So you add all the points, but only those with rational coordinates, and you add also a point at infinity. That's what is this space. Now, it is relatively easy to see. So that group doesn't act on this, but SR2Z does act on this. Because when you exchange something that has rational coordinates, you still get either a rational number or infinity. So you can extend the action to H, and that provides a compactification. So there is some topological work to be done, but this is like the projective, the Riemann sphere or the projective line. Now you look. What you want to look at modular form for more general subgroups. So I need to erase something. Well, I will erase this and this. So a modular form, to be more precise, satisfies two conditions. Well, in some sense, it is almost invariant under this transformation. So more precisely, there is a weight k such that this is multiplied by this. So that would be the first property of modular forms. And then there's the second condition that I will almost forget, which is, so that's the first of the axiom. And the second, I will write it quickly as this, the limit when the imaginary part of Z goes to infinity of C Z plus D minus K Fz exists. This is essentially a condition that says that when you go to the point of the boundary of the Riemann surface, it converges to some value. So you can extend holomorphically to the whole Riemann surface something. So this is this condition, and if it's zero, then I will say that the modular form is parabolic, or cuspidal, perhaps is. Well, it was for a long time called parabolic, and with Langland's terminology now it's called the cuspidal. But it's the same word. Well, the same object, not the same word. So and this function, I should say, so A, B, C, D, so belonging to gamma. So I will write Sk of gamma. That will be the space of cuspidal or parabolic modular form is included in this state. And okay, this is a definition that works for actually any discrete subgroup, any subgroup gamma of SR2Z. And I will concentrate on the following example, which is classically denoted gamma naught of n, which is, well, the matrices in SR2Z such that n divides C. So this coefficient is 0 modulo n. For those who know elliptic curve, this is the group that enables to parameterize elliptic curve plus a cyclic subgroup of order n. This is exactly the group that occurs. So Just like if I take the quotient of H by gamma naught of n, I get an affine curve which is called y naught of n, and if I take H star, then I get a projective curve which is denoted x naught of n. So this one is affine and this one is projective. Now I can start looking, so of course I have kept for some moment to explain that this equation looks like this one if you take the transformation 1 minus 1. It gives you something that looks like this. Now, if you have this, well, the first thing to observe is that the elements belong to gamma naught of n. So f of z plus 1 is equal to f of z. It's a periodic function. Well, if you write this equation for this matrix, you get that. Oops. Thank you. So that means that you can write f of z as the sum of, it's classical to denote this by n, by qn, where q is exponential of 2 pi I z. That means just writing the Fourier expansion of the function. So it's a nice way to look at the coefficient. And if f is cuspidal parabolic, it implies at least that a naught is 0, the condition at 0. There are further conditions because when you take gamma naught of n, there's various cusps, but at least one of the conditions will tell you that a naught is 0. And so you can at least you can associate an L function. Well, just you take the coefficients. This is just a definition. Now, it's easy to see that this is a vector space, so you can't expect good properties from those functions for any f. You have to choose sort of f's that have proper directions. And the classical way to do this is via Hecker operators. They are not exactly the same Hecker algebra as in Kazhdan course, but they are related abstractly. Anyway, the definition, the quickest definition of Hecker operators is the following in this context. So it will give a transformation of Sk to Sk. And I give it on the coefficient is that the nth coefficient of T P of F is so ANP of F plus P K minus 1 of A. So I will write it like this. This means that this is 0 if this is not an integer by definition. And this is for P not equal, well, not dividing n. You need to do something different from this. And otherwise, a n of TPF is just a np of f, of course, for P dividing n. So of course, giving the formula doesn't explain where they come from. If you have the interpretation in terms of moduli space, maybe I will just make the drawing here. If you have an elliptic curve and a pair, and this group is a subgroup of the elliptic curve, which is cyclic of order n. Then you can apply a transformation which will be well. One way to write it is, for example, E over G, and here you take, well, the full kernel divided by G. So it is easy to see that this is again an elliptic curve, and this is again a cyclic subgroup of order n of this. So if you translate this correctly, you get actually this transformation here. Perhaps I won't say more about this. Otherwise, if you have this definition, then it's a tedious computation to check that this transforms a modular form of weight k into a modular form of weight k. It's a bit tedious because you don't see why is this true, but it's true. It works. It's an easy computation. So the main theorem is that sort of the algebra generated by the TPs. So maybe I'll call them, well, you can call them TP, but I'll distinguish them. So this is for P not dividing n, and this is for P dividing n. This whole algebra is commutative. Again, it's not difficult to check. You don't see why that's true, but it's easy to check. The good thing now, if we have a commutative algebra of endomorphism of this, is you can simultaneously diagonalize them. So suppose now that F is an eigenvector for all meaning that Tp of F is some lambda p F, and same thing for UP. Well, then, first of all, you have that the coefficients AP of F essentially are equal to the lambda p, multiplied by A1 of F. So that, again, is an easy computation that I don't do. So, of course, it's natural to assume that A1 is equal to 1. You can, of course, always do that by dividing by A1 of F, and A1 of F is not 0 because otherwise everything would be 0. I'm taking an eigenvector by definition is something non-zero. Now, what can be shown is that in that case, so for such F, so if I take normalized F that is an eigenvector for all the Hecke operators, then it's almost again a formal computation to show that the L function can be written like this. It is the product for P dividing n of 1 minus AP P minus S minus 1. And it is the product for P not dividing N of 1 minus AP, P minus S plus P K minus 1 minus 2S minus 1. So this is essentially because, well, this gives a recursive formula for the coefficients APN. And the fact that those two commute means essentially that the AN are multiplicative if M and N are coprime, AMN is equal to AN. So that gives you the Euler product, and the recursive formula gives you that the Euler factor has this shape. So I've erased the formula for the L function of the elliptic curve, but I hope you remember more or less it. So if K equals 2, this is exactly the shape of the L function of an elliptic curve. So that's the first thing. The other thing is that, well, we still don't have a functional equation for this L function. We need one more thing for that. I will erase this. Well, we would like to have, suppose we had this formula that F of N Z, I will write it directly, equals epsilon N, that doesn't write very well, N K over 2 Z K F Z. Then, with that formula, so this is the formula that we can obtain. What is not obvious is the powers that I put, that you have to make a small computation to see that it says. But if you have this formula, then I will show you, you can make more or less the same computation, and you will show that the L function has a nice functional equation. Now, where does this come from? Well, this transformation corresponds exactly to Wn, which is, 0, 1 minus n, 0. So you notice one thing, that this matrix is not in SL2Z. Well, it's not in SL2Z because the determinant is n. So it's in GL2 plus Q, but not in SL2Z. But the nice thing is that if it's a small computation, is to show that it normalizes this group. Actually, all I need is inclusion, but then automatically it has to be equal. Once you have that, and that again is an easy computation, you see that Wn defined. The other thing is that Wn square is just minus n, the identity. So of course Wn square acts as identity, because homomorphism acts by identity, but almost by definition. So this tells you that Wn gives an involution on, well, Sk or Mk. Here I'm interested in Mk. Now all involution you can decompose into a plus and minus part. So you can write Sk as Sk plus or Sk minus, let's say, the kernel of Wn plus identity plus the kernel of Wn minus identity. And now, if you do the computation, you end up that those elements that sits in here or here satisfy that equation. But only if they sit in the kernel of in one of the two kernels, of course, not if they are a mix. So there would be one more thing to prove that is a little that part is a little complicated. Is that you have, this is a theory of new forms. You have eigenvectors. You can write again a basis of new forms that are eigenvectors for all the Hecke operators and sit in one of the two. So I will take that for granted. Now, the last thing I want to explain is that if I have, let me give a name to this equation. Now, so for such f, I have, if it's an eigenvector for all Hecke operators, the L function has this shape. So if further f satisfies this, so that means it is an eigenvector for this involution, then it satisfies the functional equation. Then, well, if we define LFS as n to the power n over 2 pi minus s gamma s gamma SL S, then, well, no, not L, I should write lambda, then lambda of K minus S is equal, well, there is an epsilon that comes from here, and I get I to the power K lambda S, where I write for short lambda S instead of lambda Fs. So the computation is almost the same as the one we did for the zeta function. Perhaps I will skip the details of the computation. I will just give the main. Have I written it here? Okay. The first thing to do is you write this like that. So you have the ns over 2, and you have the integral. So you get of fit s dt over t. So I skipped this part because it's almost the same as the computation I made. So instead of having coefficients 1, you get coefficients an, and the series are convergent. And the things now, you split the integral from 0 to 1 over square root of n, and the change of variable that you do now is you will write u equals 1 over nt. This is exactly the fixed point. Well, if I plug in t equals 1 over square root of n, I get again 1 over square root of n. And well, then you will use this functional equation, and perhaps I'll write straight away the end result. You get the integral 1 over square root of n, infinity. So you get this f of it. And here what you get is I to the k epsilon n k minus s over 2 t k minus s plus n s over 2 t to the s dt over t. The computation is almost the same, except that here it's a Mellin transform of the full modular form. There's no correction. So you get something that is an entire function. Now, if you look at this integral, this defines, so of course, all this is done for this where the series is absolutely convergent. So in the beginning, it's done for real part of S strictly greater than 3/2 for the computation to be valid. But after that, you look at the formula, and this defines an entire function exactly for the same reason, essentially because the first coefficient here is 0. So when you plug in, so exponential, so the first term will be a1 exponential 2 pi I it, so it will be minus t, and this is fastly decreasing. So this gives you an uniformly convergent integral, so it defines an holomorphic function everywhere. And well, the exchange, the fact that when you exchange k minus s and s, you get essentially the same thing, should be obvious. If you exchange s and k minus s, you exchange those two, so you get a little factor that switches, but that's taken into account with this formula. So for k, so you see that I will summarize this like that. So the L function, so for f, which is eigenvector, let me define this as a complete eigenvector. So I mean for TP, UP, and WN. So in the literature, that's defined more properly as a new form that verifies all this. Well, has all the properties. So has the L function has all the properties of L E of S. Well, of course, when K equals 2. For the other values of Q, actually modular forms are extremely interesting, but you get something else. And so that was observed many years ago by Shimura and Taniyama, who made sort of the bold conjecture that actually it's not a coincidence because the two objects are the same. And the theorem of Wiles is that, well, if E is an elliptic curve, there exists such a an f such that the L function is equal to the L function of S. So the L function is not cited explicitly in Wiles' paper, but it's clear that he has that in mind. Actually, the proof is comparing the Galois representation of the two. But I won't deal into that. But I wanted at least to explain where it comes from. Why, when you say something is modular, so this is a possible definition of what it means to be modular for a curve. if there is a modular form such that the L function is equal to the L function of the modular form.
It's like two questions, but if you do not want to do not answer, the first one, the function equations for the L function associated to a variety of zeros. It was a symmetry around the initial number, which is the cohomology group plus 1.
Yes.
And say for the elliptic curve, for the first cohomology, it was a symmetry around the 1, 2. The modular forms, it's a symmetry around the point, which is the weight.
Yes.
Why it should be, why the weight is parallel to the number of
yeah, that's an interesting. To give really the answer, I would have to define L function of a motive. But okay, that would take me very far. In some sense, so this modular form of weight 2, they correspond to holomorphic differentials on the modular curve x naught of n. The weight k, they live something in the cohomology of the product or the symmetric product of x naught of n. That's why they end up with higher.
Last group, and it said that it gave a different formulation, that if E is elliptic curve over Q, then it is covered by some modular. Question: if we know that, naive question, why would it follow that the function?
Oh, that's again not so easy, but that's easier. That's much easier than while if you have. So maybe I can erase this. So this is one of the possible formulation of being modular for a curve. Another possible definition is the existence of a morphism from phi to E, a non-constant morphism, of course, and then it has to be surjective. So if you know that, what you can do is the following. You take, there is essentially a canonical holomorphic form on E. At least over Q there is a canonical form. The space of holomorphic. Yes. The elliptic curve is of genus 1, so the dimension of the holomorphic differential for one differential form is equal to the genus, so it's equal to 1. So it's a vector space of dimension 1. So if you insist that it is integral at all points, it's unique. But anyway, you could also put any differential form, and then you get a differential form like this on x naught of n, and now you know that it must be equal to some fz dz on that.
Why is it why is it
Okay, that's the part that's not obvious at all, but at least you get some fe, which is in S2 of gamma naught of n. So in some sense, having a morphism like this already gives you a modular form. So you're in a much better shape to show. Now you still have to show that it's an eigenvector and to show that the L function coincide. That's not easy, but it's much easier than the Wald's theorem. So I hope that gives an idea of how those things patch together. So I wanted to finish with something perhaps a little easier that will be just the philosophy of those L functions I mentioned in the beginning, but I was scarce with example how you apply this, how you apply special values, how. So I said that the L function, of course, can be used to prove analytic asymptotic result. That's like the prime number theorem, or of course much more general results. But what are sort of the interesting special values? So I will give two examples. So the first one is the Dedekind zeta function. So if I have a finite field, this is classically called the zeta function. I have defined it earlier. So it's a product of, well, for all the prime, non-zero prime ideals or maximal ideals of the ring of integers. By the way, in that case, the functional equation is known. So the correct analog of the function psi is you multiply by the discriminant of the field, power s over 2. Well, there was this factor was for the zeta function, the Riemann zeta function, and we had this factor for the L function of an elliptic curve, and the power you put here is R1 and R2. Yes. So R1 and R2, are you all familiar with this notation? It's a number. When you have a number field, you can embed it into R sometimes, or sometimes you can only embed it into C. And then if you can embed it into C and not into R, you have the embeddings come by pair. I mean, if you have a polynomial with coefficients with coefficients in Q, when you factor it over C, you have the real roots, and then you have the pair of conjugate complex roots. That's about the same. So there is R1 of them, and here there is R2 pairs. So in total, R1 plus 2 R2 is just the degree of the field. So the functional equation in this case reads that psi k of S is psi k of 1 minus S with analytic continuation. And just like the zeta function, it has a pole at S equals 0, S equals 1. Well, the zeta function has only a pole at 1, and this one by symmetry has also a pole at 0. And so the most interesting quantity is the residue of the function zeta k at S equals 1. And it's a beautiful formula that relates, well, you have the class number, the regulator of the field, the regulator of the units, over the square root of the discriminant. And then you have small terms that would be 2 pi R2 and 2 R1. And you have to divide by the number of roots of unity. Sorry? Okay. So there are two things that you might not know. Is what is the regulator and what is the class number. So the class number, I think I already defined it. It's just the number of ideals modulo principal ideals. Or it's a cat, in that case the Picard group is finite. What is the regulator? This is something that describes units. So in general, what is called the regulator is the volume of some lattice. So I need to define what is the lattice I'm considering. The lattice to be considered is the group of units, which you can map by a map I will call log into, well, first you map it into R1 plus R2. Well, 2 points X, you take the log of the absolute value for all the embeddings. Sigma X. Where I take that is, I take all the real embeddings, and I take only one in each pair because they would give the same. Now it's easy to see that the image is discrete. The kernel is exactly the root of unity. I will call MK. So in that case, I get, if I divide by the root of unity, I get an embedding. Now, it's not exactly a lattice in that. It's a lattice in a hyperplane because this satisfies the equation y1 plus yr1 plus 2y r1 plus 1 equals 0. Because the norm of the unit is 1. When you take the product of all the embeddings for a unit, it's 1. So when you take the log, it's 0. So it actually sits, so the image is a lattice, a true lattice, in the hyperplane. Well, this hyperplane. So it's easy to see that it's contained and that it's discrete. It's a bit harder to show that it has the correct rank. In particular, this is Dirichley's theorem that says that the rank of OK star is R1 plus R2 minus 1. So you need to show the existence of sufficiently many units. So the regulator is just the volume of that lattice. So the regulator is the volume of that lattice. Well, this. It is something that controls the complexity of units in that field. So, by the way, in some sense, what is the interest of this formula? Well, those terms are quite... Okay. I'll give two examples. Let's look at quadratic fields. So first, well, I will write like this. Imaginary quadratic field. So what is the rank of OK star in this case? Well, it's 0. It's a finite group. Well, R1 is equal to 0, R2 is equal to 1, so it's 0. Sorry? Plus 5. Okay. So in that case, the regulator is just 1. Now, more interesting case, I take a real quadratic field. Then in this case, the rank of OK star is 1. So it is generated, so OK star is actually equal to plus or minus, and then there is a fundamental unit, n, z. Well, in that case, the regulator is just log epsilon, where the generator, you choose the one that is strictly greater than 1. So when I say that it measures the complexity, the regulator in this case is just the size of the fundamental unit. And essentially, the deepest result we know about, so both the philosophy in this formula is that, well, those terms are relatively simple. They are easy to bound and are easy to compute in any example. So is the discriminant. The discriminant is essentially the parameter for the field. So we get this extremely interesting quantity. And what does analysis tells us? When I mean analysis, I mean complex analysis. If you study the Dedekind zeta function from an analytic point of view, so we have bounds, we have functional equations, so we can bound it from below. What you can show is that the residue of this function, the s equals 1, well, is, say, smaller than some constant. Well, actually, you can show the log of the discriminant to some power here, d minus 1, if d is the degree of the field. And that's not too difficult. Much harder is to show that this is actually, well, it can greater than d minus, I will write this as minus epsilon. So for all epsilon positive, you can write such a lower bound. This is the so-called, essentially, Brouwer equal. So doing harder analysis, you can show that. And what do you deduce then? Is the following nice thing is that this product behaves like the square root of the discriminant of the field because of this formula down there. So I will write it like this, that the log divided by the log of the square root of delta. Well, it tends to 1 when the discriminant goes to infinity. It goes to 1. So that's, roughly speaking, the product of the class number times the regulator is equivalent to the log of the discriminant. So this is obtained by sort of dirty analysis and a beautiful algebraic formula in some sense. But it's really the combination of the two. Now, this is a deep result. If you look at those two things, it tells you right away, for example, that the class number of an imaginary quadratic field goes to infinity with d. And it goes to infinity roughly like square root of d. Okay, there's no algebraic proof of such a thing, or even an algebraic proof that would say that the class number goes to infinity. You have to use analysis so far. For real quadratic fields, it also tells something very interesting, but it's not as precise. It tells you that the product of the class number times the size of the fundamental units grows like square root of d. But it doesn't tell you which, or even if it's true. And actually, it's conjecture that it's balanced, that, well, it's known that you can construct real quadratic fields with class number almost equal to the square root of d. It's conjectured that there should exist a number of fields with log epsilon almost like square root of d, but that's not known. So I wanted to give at least this example where you see a combination of, analysis in the sense of where you write bounds, you residues, etc., and you combine this with special value to obtain interesting result. I will finish with, what would be the analog for elliptic curves of that? Well, unfortunately, you run into a famous conjecture. So that looks a lot like this, but it's not a theorem. It's a conjecture. It's a Birch-Swinnerton-Dyer conjecture. So I will state the Birch-Swinnerton-Dyer conjecture. So I set it only for elliptic curve over Q, which is actually the original conjecture. You can formulate it for abelian varieties of a number field, but there's two parts. The first part is that the order of vanishing at S equals 1. So you notice that you again have the philosophy here. The picture was like this, and you have that's for the zeta function of Dedekind or Riemann zeta function. Here you have the nice half plane of convergence. And here the interesting things occur at the edge. That's where you have a pole, and that's where the residue is most interesting. So you need just to extend a little bit the zeta function to have that. So in some sense, it's a bit easier. Now here, for the L function of the elliptic curve, the abscissa of convergence is at 3/2. And then, so here you have the nice Euler product converging. The functional equation tells you what happens here. And now you want to look at the center here. So it's going to be harder because you're far from where it is defined by the series. Now the conjecture is that this is equal to the rank of the model Veil group. So E of Q is a group. It's a finitely generated group. It has a rank. So there is, by the way, if you compute the functional equation of zeta k, you can see that the order of vanishing of zeta k, so at S equals 0, is exactly equal to the rank of OK. That's because of the functional equation. So in some sense, it's an analog of that. But there is also an analog of the class number, regulator, and all that, and I will finish on that. So the second part of the conjecture gives the leading term. So the limit of L E S minus 1 R as S goes to 1. So we have something here that is called the Tate-Shafarevich group. We have also a regulator. So I will write it like this. It's a bit, no, perhaps I should, that's really an exaggeration. You have a period. So that's really like 1 over the square root of the discriminant. And then you have, let's say, small terms. So the small terms here is some product for P dividing N. And you have here the number of torsion points to the square. Now, what are all these things? That would be perhaps a bit long to all define. Let me say that everybody who does number theory and knows nothing of Russian knows at least this letter, because we always denote it sharp, in honor of Shafarevich. So I should also add that in general, it's not known that the Shafarevich group is finite. Unlike the class number is always well defined. This is conjectured to be a finite number, because this conjecture is really far from being proven. But let's say conjecturally, it's a cardinality of a finite group. This regulator is also the volume. I mean, you have you can embed so E over the torsion you can embed into the real vector space like this. That's just formal. What is not formal at all is that you have a quadratic form, which is the height function is quadratic. The canonical height function is quadratic and gives you a quadratic form on this space. So this is a lattice in that's just formal. And the regulator is, the determinant of this quadratic form with basis, if you take for basis, a basis of that. Omega is essentially the integral over ER of the one differential form. So those factors I won't define, but they're essentially small numbers. So this leads to, first of all, proving this, would make rich the person who would prove it. But more impressingly, it would sort of unravel many of the mysteries of elliptic curve. It will sort of fulfill the basic idea behind zeta function, that you put together local informations that are relatively trivial, and by constructing this global object, you expect to discover global properties. And clearly the rank of the elliptic curve is something you want to compute, and it would give a global explanation of it. Further, if this formula is true, then in the same way as, not exactly, but in a similar way as the Brouwer-Siegel theorem, you can get bounds for the product of those two terms. Because this is essentially the inverse of the height of the elliptic curve. It's not equal, but it's let's say if I put a triple, it's almost equal to the inverse of the height. So it really behaves, you should look at it as the analog of the stem 1 of the square root of discriminant. So, for example, it is possible to prove, so if you accept, unfortunately you have to accept Virchow's entire conjecture plus the Riemann hypothesis, then you can show that this product is bounded by the height to the power 1 plus epsilon. So maybe I should write this formula. So if you accept those two, so the generalized Riemann hypothesis, of course, is the fact that the zeros of the L function should be on this line. Then you can show that the cardinality of Shafarevich plus the regulator is smaller than, some constant that depends on epsilon, the height of E, 1 plus epsilon, essentially by combining this special value with analytic bounds for the L function. If you don't accept here, you get a bigger exponent, of course. And this really should be the correct exponent. It seems, nevertheless, it seems not true that you have a lower bound here. Essentially, because you're not in this situation, but you're looking at things in the center of the critical strip. But sort of lower bounds, that's still an open question. Okay, well, maybe I'll stop here since I don't want to extend it since it's the last course.